Hello everyone. Welcome back to Dr. Liu's VCE Physics channel. Today, let's learn together about the VCE 2025 Physics examination. We will focus on questions related to the magnetic forces. My explanations may not be perfect. If any teachers, parents, or classmates find errors, please feel free to provide your guidance. A long straight wire carrying a current of I1 lies in the same plane as a rectangular loop of wire that carries a current of I2, as shown in the diagram below. Which one of the following best gives the direction of the force on the two sides of the loop, side X and side Y, due to the current in the long straight wire, I1? To find the force on each side of the loop, we must first establish the environment, the magnetic field, and then determine how the loop's current interacts with it. 1. Determine the magnetic field. Before finding the force, we must know the direction of the magnetic field created by the long straight wire. Principle: right-hand grip rule. Application: point your right thumb in the direction of the current, upwards. Your fingers will curl around the wire. Result: on the right side of the wire, where the loop is, your fingers point into the page. 2. The force on side X. Now, we calculate the force on the closest part of the loop. Principle: right-hand palm rule. Fingers, field B point into the page. Thumb, current I2 points upwards, direction of side X. Palm, force F pushes to the left, towards the wire. Observation: since I1 and side X are flowing in the same direction, they experience an attractive force. 3. The force on side Y. Finally, we look at the far side of the loop, side Y. Since the current passing through side Y is opposite to that through Y, the force on side X should be opposite that on Y. Side Y should experience a right force, or repulsive force. The correct answer is B. In physics, when we describe fields like electric, magnetic, or gravitational fields, we use specific terminology to distinguish how they behave over time versus how they behave over space. Breakdown of terms. Static field. The word static refers to time. A static field is one where the properties, strength and direction, do not change as time passes. Therefore, the strength of the field is constant over time. Non-uniform field. The word uniform refers to space or position. A uniform field looks exactly the same everywhere in a given region. A non-uniform field, therefore, varies across the region. Its strength or direction changes depending on where you are standing. Why B is the best fit? The strength of a field is constant over time, so it is static. But a field varies across the region, so it is non-uniform. The strength of torque is proportional to the number of turns, N, the strength of the magnetic field, B, and the value of the current, I. We can test each option against the torque formula. A. Increase battery voltage. This increases the current, thereby increasing the torque. B. Increase magnetic field. This directly increases the torque. C. Increase resistance. This decreases the current, which decreases the torque. D. Multiple turn coil. This increases the number of turns, thereby increasing the torque. The question asks which modification would not increase the torque. Therefore, C is the correct answer to this question. To find the direction of the force on a moving electron, we apply the right-hand palm rule by orienting our hand for a positive charge. Field B. Point your fingers into the page, along the magnetic field lines. Velocity V. Since the right-hand rule applies to positive charges, and this is a negative electron moving right, your thumb should point to the left, representing the equivalent conventional current. Force F with your fingers into the page, and your thumb pointing left, your palm pushes downwards. Conclusion: therefore, the magnetic force on the electron is directed toward the bottom of the page. For a charge moving in a circular arc within a magnetic field, the magnetic force provides the necessary centripetal force. Equate the forces. By setting the magnetic force equal to the centripetal force, we establish the equilibrium of the circular motion. Rearrange for radius. We rearrange this equation to solve for the radius, resulting in the formula. Substitute and calculate. Finally, we substitute the known values for the electron's mass, velocity, charge, and the magnetic field strength into this formula to calculate the final radius. Luca and Declan are investigating how the magnetic force, Fb, on a current-carrying conductor in a magnetic field, B, depends on the current, I. A diagram of the apparatus is shown in Figure 22. It consists of a plastic beam to which a U-shaped current-carrying loop of wire, PQRS, is attached. The plastic beam is slightly heavier at the left end, to balance the weight of the wire on the other half of the beam. The beam is pivoted halfway along its length. A solenoid used to produce a constant uniform magnetic field, B. With the plastic beam level, the loop, PQRS, is inserted into the solenoid, as shown in Figure 22. A very small mass, m, is placed on the left-hand end of the plastic beam. The force due to gravity, milligram, acts on this mass. A current, I, is then passed through the loop, PQRS, creating a downwards magnetic force, Fb, on the end of the loop, QR. The relevant forces on the plastic beam are shown in Figure 23. The current through the loop is adjusted until the beam is balanced and the downwards magnetic force, Fb, equals milligram. The current, I, and the magnetic force, Fb, are then recorded. Luca and Declan repeat the experiment with different masses. One, independent variable, the cause. This is the factor that you deliberately change or manipulate to see if it has an effect. In a graph, this is almost always plotted on the x-axis. In your experiment, this is the mass, m, added to the balance, as you are choosing the specific weights to test. 2. Dependent variable, the effect. This is the factor that you measure or observe in response to the changes made to the independent variable. Its value depends on the other. This is plotted on the y-axis. In your experiment, this is the current, I, required to bring the beam back to equilibrium. You are measuring how much current is needed for each specific mass. 3. Controlled variables, the constants. These are all the other factors that must be kept the same throughout the entire experiment. If these change, you won't know if your results were caused by the independent variable or by these outside factors. This is called a confounding variable. In your experiment, magnetic field, B, the strength of the solenoid's field must remain constant, length of wire, L, the segment of the wire, QR, inside the field must stay the same length. Pivot position, the balance point must not move. Parallel alignment, these segments are parallel to the magnetic field, so the magnetic force is zero. Opposing forces, any non-zero vertical forces on these opposite sides would be equal and opposite, cancelling each other out and producing no net torque on the pivoted beam. Pivoting the beam at its center is necessary for two main reasons. Weight equilibrium, the weight of the beam acts equally on both sides of the pivot, ensuring its own mass produces zero net torque. Equal lever arms, this ensures the distance to the mass, m, and the distance to the wire, QR, are identical. Consequently, at balance, the downward gravitational force, milligram, must exactly equal the downward magnetic force, Fb. Taking repeated measurements and calculating an average is essential because it reduces the impact of random errors, thereby increasing the reliability and precision of the experimental results. It highlights that while repeating measurements and averaging results can reduce the impact of random errors, improving precision, it cannot reduce or eliminate systematic errors. Because systematic errors, such as a zero offset on a scale or a miscalibrated meter, shift every data point by the same amount in the same direction, the error remains present in the final average. Correcting these requires recalibrating equipment or adjusting the experimental design. Note on systematic errors. Experimental reliability. Repeating measurements and calculating an average is a key practice in science, but it has specific limitations. Random errors. Repeating trials can reduce the impact of random errors, improving the precision of your data. Systematic errors. Repeating measurements cannot reduce or eliminate systematic errors. Since these errors, like a poorly calibrated scale or a zero error, shift all data points in the same direction, the error will persist in the average. To address systematic errors, you must recalibrate equipment or change the experimental design. The results Luca and Declan obtained are shown in Table 1. The uncertainty in the measurement of the current is plus or minus 0.2 A. The uncertainty in the measurement of the force is negligible. On Figure 24, plot a graph of the data in Table 1 with current, I, on the vertical axis and magnetic force, Fb, on the horizontal axis. You must include uncertainty bars and a trend line. You may assume that the trend line passes through the origin. Plotting the graph, Figure 24. To correctly plot the data from Table 1, follow these technical requirements. 1. Scale selection. Horizontal axis, Fb. The values range from 0 to 600. A suitable scale would be 1 major grid square equals 100. Vertical axis, I. The values range from 0 to 4.6 A. A suitable scale would be 1 major grid square equals 1.0 A. 2. Plotting points and uncertainty bars. Plot the 5 data points precisely: 0, 0, 120, 1.0, 240, 2.0, 360, 3.0, and 600, 4.6. Vertical error bars. Since the uncertainty in current is 0.2 A, draw a vertical line extending 0.2 units above and below each plotted point, except the origin. Horizontal error bars. Not required, as the prompt states the uncertainty in force is negligible. 3. Trend line. Draw a line of best fit, trend line, starting from the origin, 0, 0. The line should be straight, passing as close as possible to the center of all data points, while staying within the error bars. One. Identify 2 points on the line. To ensure accuracy, it is best to pick 2 points that are far apart on the trend line, point 1, x1, y1, 0, 0. Point 2, x2, y2, 600, 4.8, 2. Apply the gradient formula and substitute the values, then get the final result. To solve for the magnetic field strength, we link the experimental gradient to the physics formula. Point 1. Establish the relationship. The magnetic force is given by Fb equals NBIL. Since your graph is I vs Fb, the equation is rearranged to I equals 1 NBL times Fb. Therefore, gradient equals 1 NBL 2. Substitute value of variables and calculate. Justice. According to the formula FB equals NBIL, the magnetic force is directly proportional to the length L of the conductor within the magnetic field. Statement. If L is reduced while the current, I, and magnetic field, B, remain constant, the resulting force will be proportionally smaller. 1. Forces on conductors, Q6. Method. Two-step application of right-hand grip rule, field, and right-hand palm rule, force. Key concept. Parallel currents attract, anti-parallel currents repel. 2. Field definitions, Q7MC. Static field. Field strength is constant over time. Non-uniform field. Field strength varies with spatial position. 3. Motor torque, Q13. Relationship. Tau is proportional to NBIA. Analysis. Torque increases with higher voltage, stronger B, or more turns, N. Torque decreases if resistance, R, increases, as current, I, drops. 4. Charged particle motion, Q7A and 7B. Force direction. Use right-hand palm rule, reversing for electrons. Circular path. Equate magnetic and centripetal forces to derive. 5. Practical investigation. Magnetic balance, Q19. Variables, independent. Mass, M, dependent. Current, I, controlled. Field, B, length, L. Force isolation. Segments parallel to the field experience zero force. Mechanical design. Central pivoting cancels the beam's weight and ensures equal lever arms for milligram and FB. Error analysis. Repeated trials reduce random error, improving reliability, but cannot reduce systematic error. 6. Data and interpretation, 19ed 19G. Graphing. Plot I vs FB with uncertainty bars and a trend line through the origin. Calculation. Determine B using the gradient. Proportionality. FB is proportional to L, reducing wire length decreases the magnetic force. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.